This is the fourth lecture for 7b. It is on the errors of numerical integration and on some examples. I'm not going to derive the errors in these numerical methods. You can do that in your course on numerical methods and do it much more rigorously than is done in the book. But I'm going to point out some ideas behind them so you have a feel for why they are the way they are. The notation here is that E sub m, the subscript is giving the method. So this is the method. This one is a method for midpoint rule, trapezoid rule, and Simpson's rule. Now the absolute value of the error is less than or equal to some k. I'm going to discuss that. Some constant for each one of these rules. Now look at the midpoint and trapezoid rule. These are linear rules. Right? In fact, if you had a function, I'll write it like this, and say the function was a diagonal line, and you took the you took the area under the curve, you approximated it by the midpoint rule or by the trapezoid rule, you would get an exact fit. All right. Where you get the error is because the function is doing something like this. It's because, in this case, its second derivative is not 0. If the second derivative is 0, you get an exact fit on these two rules. The error has to do with how much of a second derivative you have. So this constant k is determined by the absolute value of the second derivative, and we look for the greatest value of the second derivative on the interval AB. And this will give me the upper bound for the error, right? At least it's one term in it. Both of these depend on the second derivative. They're both linear, and by the method of approximation, if you did not have a second derivative, where the function does not have a second derivative, these are an exact fit. See, and k would be 0 and your error would be 0. There's other terms also involved. We have, that didn't work. Let me change color here. Okay, we have the width. So if you're trying to use the midpoint or the trapezoid rule over a very large range, like from 0 to 100 compared to 0 to 5, you're going to get a bigger error. And so these appear to the third power. Then it's divided by a constant times the number of meshes squared. Okay, if you remember, the h, the size of the interval, is b minus a over n. So for these, we can factor out the mesh size. So now look at what you've got. The smaller the intervals, the subintervals, the smaller the error. That's the mesh size. Or you could look in terms of the number of meshes. If n is big, the error is small. In both of these the same way. Okay? Step size small, error small. And so that makes some intuitive sense for us, right? And then you use these expressions, and I'll show you later how to use them to calculate the step size for a given error. Now let's look at Simpson's rule. Simpson's rule is already a parabola. The error here doesn't occur with the second derivative. That's actually fit. What it occurs with is the fourth derivative. So you see, for the Simpson's rule error, this constant k is determined by the fourth derivative, the maximum value on the interval. Again, we can factor out the step size, and it goes as the step size to the fourth. Okay. All this looks a little complicated when you first look at it, but I hope by just kind of dissecting it a little bit, it will become clearer. Now I'm going to run through an example using 3 numerical methods to compute an integral for which we know the answer. If I integrate x to the 5th between 2 and 4, the answer is 672. On this slide, I've just written a summary of the rules: the midpoint, the trapezoid, and Simpson's rule. And here you might recall the pattern for the trapezoid rule with the 2's. Okay, and here's a rule with Simpson's rule with the 4-2, 4-2, 4-2, 4 pattern. All right, so here are the three methods that we're going to use. I'm not going to calculate every little number in detail, but you also have this in the written lecture, and you can trace through it yourself and compare. So for all these, I'm going to use a very coarse mesh. I'm going to let the number of meshes be 4. The step size is then 0.5. So if I calculate the values of x between 2 and 4 for n meshes, x naught is 2, the endpoint x 5. No wonder, I really can't count. I'm going to fix this up. 3. Wait a minute. 2. This is funny. Okay. x0 is 2. The endpoint x4 has a value 4 because we're integrating from 2 to 4. Right. Now, using a step size of 0.5, you can fill in the other places, the other points in between. For the midpoint rule, you needed the rule in the middle, right here, at 2.25. So here, get the function at 2.25, 2.75, 3.25, and 3.75. That's the value of the function. Now, the integral is approximated by the area of all these little triangles. So it would be the first one, f at 2.25, that's the height of the rectangle, times 0.5, which is the width of the rectangle. Then you would have f at 2.75, the value of the function there, that's the height of the rectangle, times the width of the rectangle, etc. When you add all those up, your answer is not that bad. 660. It's off by, and this is just a crude error, not the relative error, it's off by about 12. So that's your midpoint calculation with a very coarse mesh of 4. Now we'll look at trapezoid rule and Simpson's rule. Both of these require the value of the function right on the mesh boundaries. So f at 2 is 32, f at 2.5, 3, 3.5, and 4. So I just calculated those out in a list. Then for the trapezoid rule, I have to combine them using those, remember the interior points were multiplied by 2s. Add them up, and here's the answer for the trapezoid rule. About 689. The error here is in the opposite direction from the midpoint rule, and it's a little bit bigger. It's about minus 17, where we had plus 11 for midpoint rule. Now look what we get for Simpson's rule. Simpson's rule, we're using the same values that we did for the trapezoid rule. The only difference is we're dividing the step size by 3, and then we multiply in this pattern, 4, 2, 4, 2, and the answer, just in just a crude error, is off by 0.25. That's an enormous improvement. Of course, the error has a little bit to do with the function. If you remember the second derivative and the value of the fourth derivative in those error estimates on the first part of this lecture. All right, so that was an example that I did here just to show you how it would work. And now I want to do something else. I want to hold the method constant and change the number of meshes. Remember, in our work that we did, we started with 4, and now I want to increase 10, 100, 500. And I did this. I used a computer to do this, of course. Let's just look at the trapezoid rule and Simpson's rule. So here's a value. Remember the exact value is 672. And you can see Simpson's rule, of course, doing nothing but getting better, but it started off pretty good in the first place. Trapezoid rule also gets better, but it's a lot slower. For example, at 672, you are at about the same point with trapezoid that you were with 10 meshes at Simpson's rule. Of course, you can scale this up, and it doesn't take much imagination to realize how much more computer time and problems actually that you have when you're trying to go over 500 meshes instead of 10. So you can see the advantage of Simpson's rule, and you're using exactly the same points, just dividing the step size by 3 and then using a pattern of 2 and 4 on the interior points. So actually Simpson's idea was much better. And now we're going to do the other, I'll show you the other use of those error estimates, and that is to use the error estimate to figure out how big of a step size you need to hold a certain tolerance, to keep your results under a certain error. In some calculations you might say, I can an error of 10 to the minus fifth is necessary. Other times that error might end up being squared and put in some other function, so 10 to the minus 2 might be okay for you. So depending on your problem, you pick the error that you can live with. All right. And now we have to pick the step size based on the method to give that error. So this is how we do it. If you remember, for the midpoint and trapezoid rules, the error was based on the second derivative. So we start with a function. In this case, we're doing the same function that we did before, x to the fifth. All right. And now to find the, there was a k value in each one of them. For Simpson's rule and trapezoid rule, it depended on the second derivative. For midpoint and trapezoid depend on second derivative. For Simpson's rule, it depends on the fourth derivative. So we go ahead and take those derivatives. This is a point that students might have a little problem with. Let's take this derivative. We know what it is. It's 20x to the cube, x to the third. We need its maximum value on the interval 2 to 4. How do you find that? Well, a lot of times you can find it by thinking about it. X cubed is maximum, has its largest value where? When you're thinking of 2 to 4, it's going to have the largest value where x has the largest value. That would be at 4. Remember, this will be taken in terms of absolute value, so think in terms of absolute value. But it's going to be greatest when x is 4, so evaluate that second derivative at 4, and here is going to be the value of k that we're going to use in that error expression in the first part of this lecture. For Simpson's rule, it was based on the fourth derivative. Here's the fourth derivative. Okay, it's 120x. Where will this have its largest value? At x equal 4. So we evaluate it there and get 480, and this is the value of k. All right, now we have that. We're going to go back to those original expressions. Okay, so here we are with those original expressions filled in. Let me write it out for the numerical. For one of them, say the midpoint rule, it was a k. They depend on the second derivative, b minus a, h squared, all divided by 24. Okay, that was the error for the midpoint rule. All right, so I'm looking for the step size. So I'm going to substitute all my numbers into here that I know. I know that k was 1280. There it is. b minus a is 4 minus 2. 24 I know. I don't know h squared, but I know I want this error to be less than 1 times 10 to the minus fifth. So I solve for h, and I can turn around and solve for n, and I need a mesh that gives me 6,532 subdivisions for the midpoint rule to have an accuracy of less than 10 to the minus fifth. If I go through the equation, the same exercise for the trapezoid rule, I find I need 9,238 subdivisions to hold that kind of accuracy. But now look what happens for Simpson's rule. Simpson's rule, the expression for the error is less than k, which depends on the function, the fourth derivative of the function. And we have b minus a, 180 here, and h to the fourth. So you can take the fourth root when you get done with all this. Okay, again we want the error to be less than 10 to the minus fifth. When I solve for h, I find that h can be fairly large, and n of 54 will give me the same error. So that is how you use the error expressions to find the step size and the number of meshes that you need to numerically solve that problem.